So you have 10 minutes for presentation, and this is the call, and I will give you 2 minutes warning before the end. Okay, let's start.
Good morning, Professor. I'm Alice Yu Q of Team 10051 from St. Francis Canossian College, and the topic I'm presenting today is an investigation into gamma function. So this is the contents of my presentation. Our initial aim of this study is to explore the properties and consequences of gamma function. And in most tests about gamma function, but this is quite broad, so we then motivated to work on something more specific. So we see that in most tests about gamma function, the value of gamma 1 over q, where q is an integer, is not usually discussed except for q equals to 2. Therefore, we would like to investigate the values of gamma 1 over q for q equals to 2 and other values as well. And in this study, we have asked these questions and we obtained these results. And before proceeding to the proof of results, I will first give a definition of gamma function. So gamma function, gamma x, is divided as this integral and for real x, although this function can be extended to a complex plane. The main result of our study is in section 3.3 in my paper, and we start our study from a question posted in the book Special Function. And this is the original statement I quoted in this PowerPoint. Noticing that 2I equals to gamma 1 over 2 equals to root pi, we thought of using this to prove the particular value of gamma 1 over 2 equals to root pi. So what followed was just some routine calculation, and here is the proof. And we consider the integral I equals to integrating e to the power negative x squared from 0 to infinity. And by simple substitution, we obtain that I equals to 1 over 2 times gamma 1 over 2. And we denote it by 1. And so we then consider the I from another way, that is to consider I squared. And we obtain this, and this step is followed by Fubini's theorem. And so we would like to evaluate this integral in the polar plane, and we define the following. And then the region D becomes this. Then again, by Fubini's theorem, we can rewrite the integral I squared like this, and we multiply a determinant equals to R because of the change of variable theorem. And so we are now managed to evaluate I squared. And so I squared equals to pi over 4, so I equals to root pi over 2. And by 1, which we denoted before, so gamma 1 over 2 indeed equals to 2I equals to root pi. And so we obtain this result, but what to do next? It's very natural that after evaluating the case when q equals to 2, we would like to further investigate whether it's able to evaluate gamma 1 over q for other integers q by a similar method. So to achieve this, of course, we first check that we can express the gamma 1 over q in such form, and indeed we can. And so we have gamma 1 over q equals to q times integrating e to the power x to the power q from 0 to infinity, and we denote this expression as 2. But unfortunately, we cannot evaluate this integral for q other than 2. So we thought of approximation. And to have a clear picture in mind, we plot the graph of the integrand, and we observe that using such expression may have the advantage. For instance, to approximate gamma 1 over q, we can consider the two expressions, the traditional expression or our expression. So the first integrand diverges as 0. This may cause trouble in approximation, while the second one, that is our expression, converge for all values in 0 to infinity. So this is the graph. This line, this curve is the integrand of the traditional expression, and this is our expression. And the traditional expression did diverge as 0. And so, but is there really a big difference? So we turn to approximate some known value, that is the gamma 1 over 2 we have just come up with. And so this is equals to this value, 2 times dp. And for 2 for this integrand, that is the integrand from our expression, is quite accurate even we just integrate it from 0 to 60 because it's converged to 0 very quickly. And for the traditional one, Mathematica still managed to give an approximation, but it's not as accurate as the above approximation. And you can see our evaluation by Mathematica. So the bottom one is the value of root pi, and the first one is the evaluation through the traditional definition, and this is our expression. And we can see that it's accurate to 4 dp, while our expression is accurate to 5 dp. So we have a little conclusion that our expression may be good when we want to approximate the value of function for integers q by numerical methods. And we go further, so we consider the sequence of function fn of t equals to e to the power negative t to the power n. And to have a clear picture in mind again, we plot the following curves. And so from the previous curves, we can know that fn converges to f equals to 1 for t greater or equal to 0, smaller than 1, and 0 for t greater than 1. And so we have the following hypothesis that is proposition 3.3.2 in my paper, and limit n tends to infinity, integrate fn equals to integrating f equals to 1. And note that we cannot say it's true directly as this sequence of function is not uniformly convergent. And so consequently, we obtain these results and 3.3.3 from my paper that gamma x diverges as 0 and all negative integers. And by my expression, we have this and take limit to infinity at both sides, and by applying our hypothesis, so we obtain that gamma 0 equals to limit n tends to infinity, and so it's indeed diverges as 0. And for the other integral values q, from the recurrent equation, we obtain gamma negative k equals to limit n tends to infinity n over negative k factorial. So the gamma function is indeed diverges as 0 and all negative integers. And we're back to our topics concerning the approximation to gamma 1 over q. So we have the claim 3.3.4 in our paper that we can approximate gamma 1 over q for large q by simply a q, because limit q tends to infinity, gamma 1 over q whole thing over q equals to 1, and this is directly followed by our proposition 3.3.2. And during our study, I mostly focus on the bulk special function. In the bulk special function, we come across another question, which is quite elegant at what is claimed in this statement. So therefore, we have included in our paper also. And the detailed solution can be found in my paper, and I will just showing you the key steps. And we first apply Lagrange duplication formula, and then we obtain this result. And by simple substitution, we can eventually express L in terms of some constant plus 2L. So we obtain the value for L. And in this, so after this project, I've got some reflection, and in this project, I've studied the gamma function, which is a special function. And in the study of special function, there is a topic called Q series, which is a generalization of the function. For instance, there is a Q gamma function of which when Q tends to 1, the Q gamma function equals to the original gamma function. And also from the book special function, I learned that Q series is useful when dealing with the problem of partition. And the proof by generating functions in partition problem is quite elegant. So I may have some studies on these areas in the future. And this is the end of my presentation, and thank you.